Perfect. Hello Quantum. Hello Quantum. Hello Quantum command line version. What I'm expecting to learn here is maybe sort of a little bit more than what you actually see in the game. I have absolutely no idea what to expect. It seems like I don't have to download anything. I can just play the game directly online, which is cool. So let's see what happens. I don't know what my expectations are beyond, beyond the Control Z, which is already what we. Okay, so press enter to continue. Choose which mode you want to play from the following list. Main tutorial, a gamified tutorial for programming quantum computers. Qubit Swapper, a few puzzles dedicated to the task of swapping qubits. Sandbox, a chance to do what you want with 2 qubits. That's pretty cool. Image Superposer, write a quantum program to create. Oh, interesting. Image Superposer, write a quantum program to create superpositions of images. Bell Test, write a quantum program to explore the unique nature of quantum variables. Cool. That's way more than I expected. I mean, let's just go one by one. So this is going to be about a main tutorial, a gamified tutorial for programming quantum computers. Number 1. Select a level from 1 to 33. Is it just in terms of basics, or just start with 1? And in these puzzles, you will see a grid and a given task. Your job is to complete the task by using quantum programming. Your first job concerns a single qubit, which we call qubit 0. The state of this is visualized on the grid using 2 colored boxes. Each is either on or off, something between. The first puzzle job is to turn the box off using the command known as X. 1X should be a north, but to make sure it's working properly, do it 3 times instead. Target, turn off the blue box and use the X command 3 times. Oh, it's a whole different type of representation that we're seeing here. So allowed operations for qubit 0, X, use exactly 3 times, or choose one of the allowed operations from the list above by typing its name below, X. So now this has turned into this thing. So X. Now it's on again. Okay. Okay, perm X, qubit 0, that's what's happening here. And X again, off. Okay. Great. The X command turns blue box on, nothing to wrap. Okay, so I think that's called qubit 1, also described because qubit different place. To reset it and to test out the X, do the same as before. Okay. Okay, I see. So what we're seeing here in the top is the qubit 0, and this is the qubit 1, and this is the grid, the equivalent grid in there. Okay, interesting. So, and I'm assuming that's the measurement on the z-axis, and then that's the measurement on, I don't know, because I don't know what it means, red, and it seems it's half full. Cool. So probably that means something like it's half full in terms of it's both 0 and 1, 50% probability. So next, X, next. Cool, great. Now we've got a hang of X. Qubit, what is a qubit? We'll skip all that. The 2 boxes represent our 2 favorite methods of extracting a qubit. Usually blue box, if it's off, we get 0. If it's on, we get 1. So it's kind of like a similar version. Okay, choose one of the allowed operations. Turn off the blue box. Next, target achieved. Great. You can also learn about how we visualize qubits at this page. That's an interesting. What is this? I might save it for later if it's, or is it? That's a new. That's a whole new. Okay, when is this? That's February 2018. It's a 12 minutes read. I mean, visualizing a pair of qubits. I'll leave that for later. I'll save the link. I'll leave that for later. Let's keep playing. So looks like the blue box turn off. The blue box. X. Great. Next cheap has a new operation enabled called H. It swaps the contents of the two boxes. To test it out, do the alt trick of repeating 3 times. Target turn off the blue box and use the H command 3 times. So if I use H, now it's off. H, now it's on again. H, now it's off. Great. Now for the next qubit. I should probably notice that the blue box is only half on. In inverse, what the box is doing, off becomes on becomes off, but the half remains half. Turn off the blue box and use the X command 3 times. So there's nothing. Okay. But if extracting an output from a box that's half on would give a random result. Isn't working on this chip, level 7. But you will have a new operation called Z. Okay, and this is what's not in the game. So this is what's not in the game, which is the Z. Because in the game we have, in the Hello Quantum game, the mobile app, we have the control Z, but we don't explore the effects of the Z as a single qubit operation. We'll need to work how to reset the qubits with Z and H. Target turn off the blue box without using the X command. Z and H. So what does the Z do? So if I, yeah, good. So obviously, the Z by itself will not do anything. But if I do first an H, now it's kind of half. So it's like 50-50, and now a Z. Don't get it. Turn off the blue box without using the X command. You'll need to work out how to reset the qubits with Z and H. It's doing nothing. Oh, wait a second. So I've done a Hadamard, then I've done a Z, and then I've done a Hadamard. Oh yeah, because that's the trick with the Hadamard, that the Hadamard on a 1 state goes to the -1, which is then. So if I apply the Z, so if I apply Hadamard and then a Z, and then Hadamard again, that is the sequence of operations that we need here. Okay. Yeah, that's cool. Now for the next qubit. The red boxes represent another way to get a bit out of a qubit. Again, off gives you a 0 and on gives you a 1. The red box can only be certain of the result it would give when the blue box is completely random. Qubits only have a limited amount of certainty to go around. The H command swaps the results you'd get for blue and red. Move the off to blue and the randomness to red. And the randomness to red. So in order to do that, I would say, if I do that, okay, yeah. So intuitively, it's an interesting way to see things. Okay, so basically, I'm still trying to fully grasp the visualization, but I think I get it. The color is just to differentiate that. That's like another way of seeing the qubit, and that's this one. the way the bar is set, I'm not so sure if that, because maybe that's explained in here, but for the moment, let's keep it this way. So great. Now the next chip, now you know the basic tools, you can tackle both qubits at once. You'll see that the 4 boxes you are used to, which represent the 2 qubits, there will be some extra ones too, but don't worry about this for now. Target turn off the blue boxes. What? Allowed operations for qubit 0. Yeah, but how can I tell which to which apply? Choose one of the allowed operations from the list above by typing its name below. Turn off the blue boxes. Interesting. So it should ignore all this stuff. So here we have on, and here we have a sort of 50-50, right? So in which case, and we have X, Z, and H. In which case I would say, or I mean, let's explore. Let's see what happens when the problem is that I can't seem to resize that. So if I press H, okay, now I say 0 or 1, say 1. Now it's fully on. And if I press now, I should be able to, now exactly, I moved. So by doing that, I moved the certainty around within the same qubit, right? If I do X 0, so now this is off, and if I press now X 1, now this is off as well, and we have achieved what we wanted to do. I'm curious about this because this is a different, now I see something. Now, you know, in the game, in the app, it's just on and off or random, and then and those things here, they're interesting way to visualize this. Let's go ahead. Now the next chip, another chip with the X turned off. So another chance to practice your workarounds. Turn off. Okay, so now I have to turn off the blue boxes without using the command X. So now we'll probably have to go around the Z and the H. So for example, for the qubit 1, what I probably should do is I should do H. What if I say H1? Does it work? No, I have to say H first and then 1. So now I've got the certainty here and the certainty here, and now I'll apply the Z to 1 and the Z to 0, right? So interesting. So here, what's happened is now what I've turned off is the sort of the information on the right circles. Okay, interesting. I'm trying to kind of work on in my head what's going on and how to describe that at an intuitive level. Because we're talking about the same qubit, right? So it's just sort of you can imagine like another dimension, right? That's the qubit in one dimension and another dimension. So basically, the Z operates in the second dimension, whereas the Hadamard is just moving certainty between the different dimensions. You could think about it this way. Maybe that works as an analogy, and that's a cool analogy, actually. We'll see. And then you could say the qubit has the 3 dimensions, so you're moving certainty around the 3 dimensions. Oh, that could be a way to think about it. Okay, and now I'm assuming that if I do a Hadamard again, I'll basically move the certainty, the little certainty that I have, to the other dimension. So if I do h1, cool, and h0, cool, and I'm done. It's almost like, so this almost felt like, and it's pretty eye-opening, so it's almost like I emptied, so to say, the certainty, because I turned things off in the dimension 2, and then with the Hadamard gate, I just moved that bit of I just moved the uncertainty around, because in the second dimension it was certainly off. Then that now is in the dimension 1. Yeah, I basically flipped that. Okay, that's cool. That's cool. Let's do a couple more levels. See what happens. Now on to the next chip. In case you are wondering about the extra boxes, they will tell us about the relationship between the two qubits. The blue one, for example, keeps track of how likely the two blue outputs are to agree. Okay. So the blue box keeps track of how likely the two are to agree. If it is off, it means that the two qubits will definitely agree. When it's on, they'll definitely disagree. Interesting. Keep an eye on how it changes on the chips. On the chip, turn off the blue boxes. So this one. So basically, what's telling us is this here. Interesting. But that's just this one, right? So it's just this one. I mean, I'm assuming that's also going to be the same, but for dimension 2, right? So turn off. So yeah. So x0, right? And now, of course, they will disagree. And if I do x1, done. And they'll both agree. Okay, great. The two purple ones. Okay, that's cool. Let's see. The two purple ones are for the blue output of one qubit. The two purple ones are, so the extra red, I'm just going too fast. The extra red box similarly looks for agreements of the red boxes. Okay, yeah, makes sense. That's what we're saying. The two purple ones are for the blue output of one qubit and the red output of the other qubit. Yeah, okay, that's also what we knew. I find it curious that here it's represented differently. And why are they inclined? Again, I'll probably should go and read that, and I'll do that in the next video. Okay, yeah. So how likely are they to agree or disagree? And it's kind of half. So 50% of the times they'll agree, and 50% of the times they'll disagree, because basically this one is always off in this case, and this one is 50% off and on. Okay. The X just doesn't invert the blue box of the qubit 0, but all the boxes in that column. Turn on the blue boxes. What do I have to do? Turn off the blue boxes. So, as I said, I'm going to basically shift the certainty with a Hadamard. I like this shifting certainty around. I mean, that makes it intuitive. And now basically I'm gonna do an X of 0 and an X of 1 off. The Z for qubit 0 similarly affects all the boxes of the other column. The Z for qubit 0 similarly affects all the boxes for the other column. Turn off the blue boxes without using the X command. I quite don't see that. The Z for qubit 0 similarly affects all the boxes of the other column. Z for qubit 0. So if I apply a Z 0, okay, in the sense that it affects that. Yeah, but I mean, I like to see it more like those things basically adapt to whatever whatever the qubit states are, rather than this operation affects everything. I mean, it's obvious if you think about how those are defined. When you affect when you change something in the qubit 0 and the qubit 1, then those are also going to change. So now they are likely, because this is on, it means they're likely to disagree. Interesting. That is interesting. And so, oh yeah, and I have to finish that with the next one. Oh, sorry, I cannot do an X. So H1 and Z1 and H1. Ta-da! Ah. Why? I thought I had moved that one there. Okay, H0. Whatever. Okay, cool. 14. I think there are 33 levels, so I'm probably going to stay at a half. The H for qubit 0 swaps the two columns. Yeah, again, I don't find those explanations so useful directly. But I know what it means. Yeah, it's just I like to see those four as basically a way to explain the relationship between those two, right? So I guess until you don't introduce the control gates that might affect those in a weird way, then single qubit operations in each of the qubits will just obviously change the values, the four values in the middle. So what am I supposed to do here? Turn off the blue boxes without using the X command. So I'm going to do an H1, I'm going to do a Z1, and I'm going to do an H1, and then I'm going to do the same here. I just have to do a Z0 and an H. Oh, yeah. I mistyped. H0, H1. Then. Great. On to the next chip. The operations for qubit 1 have similar effects, but on the rows instead of the columns. The H affects one row, the Z affects the other, and the H swaps them. Turn off the blue boxes. Yeah, okay, it's the same game over and over again. Currently, just so you can see the effects of the different rows. I wonder whether we're getting to the control Z's in the main tutorial. I hope so. So we will do Z1, H1. We're off this one, and then actually, okay. So here I just have to just say H0, and we're done. And we are done. So just do your magic. There's a nice chip with everything working. Turn off the blue boxes. Okay. So here's kind of like play around with it. Turn the things on. So actually, I'm curious about one thing. So what if I can actually just say Z1, Z0. So they're all off, and then I just do H1 and H0, and I'm done. Perfect. Let's move on. Have you noticed the program that is getting displayed as you work? This is the code you're writing for the quantum computer using the Qiskit SDK. Yeah, this thing here. Z. Yeah, exactly. Check the for more information. Yeah. Another well-behaved chip. By the way, most of IBM's chips have more than just 2 qubits. In fact, you can use a real device with 16 qubits from the comfort of your home. Turn off the blue boxes. It's again the same. Okay, I'm gonna just X0, so here we're done. And in that case, we'll just do a Z1 and a Hadamard 1, and we are also done. Now to the next chip, level 18. This chip has a new operation enabled. Control Z. Yay! Perfect. We are here. So like H, we can think of this as swapping the contents of boxes. I don't want to think about it this way. It swaps the contents of the red box of each qubit with the purple box next to it. It swaps the contents of the red box for each qubit with the purple box next to it. This swaps lets us make big changes to the way the qubits are correlated with each other. Exactly. Perfect. I'm happy because this is a nice way. Yeah, but you know, this could also be written, nice. Of course, for this reason, the CZ is known as an entangling operation, of course. The same like the control X, right? So, okay, so it enables us to do some type of correlation, which is different than the control Z, the control X. You'll probably need to use it to this. I haven't thought about that. Okay, or actually I came across that idea. I thought maybe it's used to disentangle, so you'll probably need to use it to disentangle the qubits here. Okay, let's see what we have. Turn off the blue boxes. Why can't I just use, I can't just use Z and H, because the Z in this case, let's see, if I do Z0, the only thing that happens interesting. You see, that's kind of weird because, and that's probably the hint that there's something else going on, which that's why this is not an enough representation, detailed representation. So, because when I press Z0, this guy lights up, but nothing else changes. So this means, so I'll go back to what I was, and what happens if I do a control Z? Because what this is telling me is that those two qubits, they're random, but if I take a look at that, it's telling me they'll 50% of the time agree and disagree, and then this is telling me that they will always, okay, but so there is a certain correlation, because the fact that those two purple ones are off, it means that this dimension of this qubit with this dimension of the qubit 0, they will always agree, and that one as well. Oh, nice. Okay, so they are kind of like intertwined in that sense that the qubits will always randomly show something, but like the dimension of qubit, the first dimension of qubit 0 and the second dimension of qubit 1, they will always agree, and vice versa. So if I do a control Z, so what now has happened with the control Z, we have basically, can I say we have disentangled them? Because how can I know whether something is entangled or not if there's a type of correlation? I mean, it's just, now it seems like because they are certain in one dimension. Maybe that's the trick. Because they are certain in one dimension, we can say they're not entangled. Ooh, I don't know if that's true. That could be an interesting way of seeing it. Lots of stuff we're learning today. So the control Z is for entanglement and disentanglement, and that was so what we've done now with the control Z is basically what we have done in a way is we've moved. So that's what I was trying to explain in another video. So we've kind of moved the uncertainty from one dimension to the actual correlation. No, that's also not true. And probably what's actually happening here is that we are moving that information to the third dimension, which we don't see here. Maybe. And maybe that's the damn way to see things. Let's see. So but now it's kind of easy, right? Because now what I can do is I can say I'm gonna do a Hadamard to move things from one dimension to another here, and the same here, and we're done. Cool. Yeah, well, that's way better. That's way better than the app. But I also have to say, I think playing the application first, it helps to then go through that, which explains you. I think you see things in a deeper way.